Dear ladies and gentlemen, welcome to my presentation with the topic of complete filter simulation and some highlighted new features related to filtration applications in GeoDict 2021. My name is Mehdi Azimian, and in the next slide I'm going to show the content of my presentation. Well, I will mainly talk about the filter simulation with GeoDict 2021. And with filter here, we mean the whole filter with housing. For such detailed simulations, we have now a new user-friendly graphical user interface in the GeoDict 2021. I'll also show you some filtration-relevant improvements afterwards, showing a slide regarding the improvements in calendaring or compression simulation of filter media. And last but not least, I just mentioned the topic of the exhaust gas treatment, or in general, the new features in Azimian, which will be presented in detail in the next presentation. Let's start with the filter simulation, which, as mentioned, is the main part of my presentation. So, of course, the first step to do or to conduct the filter simulation is to import the geometry of the filter into GeoDict using the import GeoCAD module. With import GeoCAD module, you can import geometrical models in CAD format, for example, in STL or OBJ file formats, and GeoDict transforms the CAD model into a voxelized structure. For this study, as you can see, we imported a CAD geometry of an oil filter into GeoDict. The flow comes here from the top, right side, and left side into the filter, and then passes here downwards at the sides, and then it can here passes through the outer plate, and the filtered oil will be discharged here from the outlet plane here on the top. You can also see an inner pleat here, and also a valve, which in this image the valve is closed, but under circumstances the valve is designed to open when the oil filter becomes clogged through the outer plate, or when the oil is too thick, for example at low temperatures in winter. So the valve moves upward, it becomes open, and the oil flow can pass through the valve, and it can also be filtered through the inner plate with a higher permeability, and the oil can pass further through the engine. This way we avoid any damage to the engine. This is again another view, or a cropped view, of the filter element or the filter, where you can see the inner plate part, the outer plate, the support meshes here, giving the shape and strength to the pleats, the valve here in the middle, and the housing. Well, each part of the filter after the import can be assigned with a correct name or the corresponding name, and with an individual material ID, as you can see here, and with an individual color. For this example of oil filtration, we used special engine oil 20W50. And then you can see also the solid parts from the housing shown here with red color, the cap with the green color, support meshes, the spring, the valve. And you can also see the porous parts, the inner pleat, shown here with brown color. This is a porous media, and this means the oil will pass through the porous media. The outer pleat is shown with a dark green color. This is also the porous part, and we also need to define the inlet and outlet planes Here again, as mentioned, on the top, right and left are the inlet planes, and here in the middle is the outlet. So for better visualization, they are not shown here. And we have an exterior as material ID 13. This is then the volume between the filter and the computational domain box. In this slide, you can see an in-through image of the filter, first when the valve is closed. So please take a look here at the valve. When I click further, the valve will move upwards a bit, and then it becomes open here. So there's a passage here that the oil can enter here and then can pass later through the inner pleat. And we simulated both cases for the current study. So for flow and filtration simulations, we consider once when the valve is closed and then when the valve is open. Right. Well, for a correct and precise simulation of the filter at macro scale, of course, the characteristics of the filter media at micro scale should be also defined. And you know that the filter media of the pleats are made whether from a non-woven or from a woven media. For this case, in this study, the filter media of the both outer and inner pleats are woven media. So for the outer pleat, we have the plain Dutch weave, and also for the inner pleat. And the information are also provided by the manufacturer. And by having this mesh description, the warp and weft diameters, by knowing the mesh thickness or the media thickness, first of all, we can model the geometry of the filter media, which is in this case is woven media. So here the filter media of the outer pleat and the inner pleat were modeled with the weave geomodule of GeoDict using the plane weave submodule. Afterwards, we simulated the oil through each of the filter medias by solving the Stokes equations with Lear solver to define the material permeabilities for each media. We considered a very low velocity as the mean flow velocity, so that we have a small Reynolds number, so that we can use a Stokes equation. And in the Stokes regime, of course, the material permeability is constant because the pressure drop increases linearly as a function of velocity. These material permeabilities for outer pleat media and inner pleat media are necessary to provide later as input parameters for the macro scale filter simulations. One more comment here, as you can see on the image at the left side, we visualize only the geometry of the media, and at the right side only the flow velocity distribution. All right. The next step after computing the material permeabilities is to run a pure oil flow simulation, so without particles, through the filter. This is the case in which the valve is still closed. So we ran the oil flow simulation with 17 liter per min. This was also provided as an information. And here for the inner and outer pleat parts, we use the permeabilities or the material permeabilities that we already computed and shown in the last slide. So here, as you can see, the flow streamlines coming from the inlet and then passing through the outer pleat, and then here are discharged from the outlet, but a small amount of the flow also pass through the inner pleat, and you can also see here some vortexes in the vicinity of valve springs. So let's see the case where the valve is opened. So you can see a considerable amount of the flow will also passes here through the from the valve, and then the flow can be passed through the inner pleat, and the filtered oil can again be discharged from the outlet plane. Of course, when the outer pleat is clogged, then probably the majority of the streamlines or the flow will pass through the valve and through the inner pleat. All right, so we did this pure flow simulations with oil and without particles to find out the average flow velocities through the pleats. So in this way, this is now a zoomed view of the velocity distribution here through the outer pleat. And with this, we can define the average or the mean flow velocities through the pleats. In this case, it was 0.01 meter per second. And this is required that we do filtration simulations later, again on the microstructure of the filter media to define the filtration behavior of the media through the depth and cake filtration regimes. So with the velocity or the mean flow velocity that we computed through the pleats, we need to run a filtration simulation through the outer pleat and inner pleat. In these simulations, we considered the isocoarse dust A4 particle size distribution and only considering the particles bigger than 10 micrometers for this study based on its application. Here we ran a lifetime single pass filtration simulations through each media, and the results after the simulations are, for example, the pressure drop as a function of time, the fractional filtration efficiencies, the deposited dust per batch and per time. And so here, for example, in these diagrams, you can see the average filtration efficiency per each particle size during the filtration simulation from the beginning to the end of the filtration simulation. So for the unresolved simulations or the simulations at macro scale or through the filter element, we need some essential parameters from the resolved scale or micro scale through the filter media. These are, first of all, the so-called maximum particle packing density, named as F maximum, and also the corresponding flow resistivity named as sigma max. And we have to define these two parameters for depth filtration and also for cake filtration. So for the depth filtration, when we reach the end of depth filtration regime or a start of a drastic increase in pressure drop occurs, the simulations should be stopped and the Fmax and sigma max for depth filtration can be defined. And by running the filtration simulation further and then having a filter cake on top of the media, the pure filter cake on top can be cropped and the Fmax and sigma max for filter cake can be also computed. So besides the fluid and particle characteristics, we need the following parameters as input parameters for the whole filter simulation. So I already mentioned we need the Fmax and sigma max for depth filtration and Fmax and sigma max for cake filtration, which can be computed with these formulas. And we also need the fractional filtration efficiencies that we computed on the microstructure of the filter media. And we also need the material permeabilities of the porous parts and their thicknesses that we also already computed these permeabilities, and we know these thicknesses. So having all this information, we can use them as input parameters for the whole filter simulation. So here you can see the filtration animation in the case when the valve is closed. So here we ran, as mentioned, filtration, a single pass filtration, 20 batches, each batch 50 seconds. It means in total 100 seconds of filtration time, and in each batch about 84 million particles are simulated, and this number is actually based on the particles concentration in the oil, the particle size distribution, flow rate, and the batch duration. So if I start the animation, as you can see here, when the valve is closed, the main filtration occurred through the outer plate, and here in this animation, the particles shown with gray color are visualized with a visualization size factor of 6 for a better visualization. So if we take a look at the case when the valve is opened, same simulation with the same settings, only when the valve is open, we can see here that the particles are filtered through both the inner and outer plates. All right, that was the part about the filter simulation. Now I'm going to show some filtration relevant improvements very briefly. So here are some highlighted filtration relevant improvements in GeoDict 2021. We have the slip lens here, not only for the flow simulation, but also in the new version, also for the particle tracker solver. Then we have the weighted particle starting positions so that we get a more realistic distribution of particles at the inlet. The third highlighted feature is the continuous injection of particles through the domain for better filtration visualization. And yeah, the fourth point is the activation or implementation of a so-called slide sieving for the particles. And of course, we have also some more tracker stability improvements in the new version of GeoDict. Well, regarding the slip lens for the particle tracker solver, as you may know, in GeoDict 2020, we had the possibility to consider the slip lens when simulating the flow through the nanofibers available in FlowDict module. So for example, here you can see an example of a 3 layers fibrous filter media for face mask. And you can see here in the middle a nanofibers layer. So for a correct and precise simulation of the flow, of course, you have to give the slip lens. This was already available in GeoDict 2020, and now in the new version, besides the FlowDict, the slip lens can be also inserted in FitterDict GUI, as you can see here. It means in the particle tracker solver, the slip lens is of course correctly implemented, and not only the flow simulation, but also the filtration simulation through nanofibers can be done more precisely. Another improvement is the weighted particle starting positions. So in the recent versions, we had the uniform placement of injected particles at the inlet plane as starting positions. But when we especially don't have no long inlet area, it's of course more realistic to set the weighted particle starting positions, like here on the right side, that we have set the velocity weighted placement for particles to be injected through the media. So if we can take a look at the animations, we can see the difference at the left side when we have uniform, and on the right side where we have the velocity weighted placement for the particles. Another improvement is the continuous injection of particles through the media. At the left side, you can see the case when all particles start at once. And on the right side, you can see the case when the particles injected continuously. So of course, there would be no difference in results. This is only for a better visualization when you want to generate some filtration animations like here shown on the right side. Improvements in slide sieving is also another important topic. Well, we have the default case in GeoDict as slide sieving off. It means the particles will lose kinetic energy on each contact or on each hit with the surface. And after some hits, all energy is lost, and the particle will get caught on surface due to low energy. So here is the filtration animation of particles through perforated plates when the slide sieving is off. So when the slide sieving is on, it means the particles will lose some kinetic energy only on primary hit or on primary contact with the surface. And after the primary hit, the energy is conserved or it remains constant. The particle will continue a sliding movement. This is the filtration animation when the slide sieving is on. Alright, here I show briefly the calendaring or compression simulation improvements when we, for example, compress a filter media. So here we can see a complex case where we have a sand control screen at the left side having 5 different layers. You can see one quite fine woven media shown with red color in the middle, 2 coarser woven media on the upper and bottom side of the red media, and on the very top and bottom sides you can see 2 perforated plates. So by running the compression simulations with ElastoDict field mass LD up to a compression of 25% at 10 steps with 32 parallel processes, we can see that having GeoDict 2021 version, the runtime is reduced by 40%, which is considerably faster. This topic will be also presented by my colleagues in the structural materials sessions. All right, I just also mentioned the topic of the exhaust gas treatment, which is also very important, and this will be presented in detail by my colleague after my presentation. All right, thank you for your attention and look forward to your comments and questions. Thank you.